Good morning, everyone. My name is Charlie Jordan, and I'm a teacher at Citronelle High School. A little bit about me before we get started. I'm a proud graduate of Citronelle, and I've been teaching at my alma mater for the past 5 years, where I teach a variety of courses. This semester, I currently teach pre-calculus dual enrollment, geometry, and Algebra II Trig, which is what I'll be teaching you today. So today's lesson is going to focus on essential concept number 1, which is focusing on exponential and logarithmic functions, specifically the graphs of those functions. Today we're really going to dive into exponentials, and we're going to determine what the graph looks like, different key characteristics such as the y-intercept, the end behaviors, domain, range, all of that fun stuff. Before we can begin though, we need to answer this very important question. What is an exponential function? Up to this point, you may have heard someone refer to something like, oh, it grew exponentially, or may have said the word exponential, but my guess is that you've probably not actually worked with it before. That's okay, because we're going to dive into it and you're going to become just as familiar with exponential functions as you are with quadratics. When you're practicing for the ACT maybe, and you see a problem, you go, that's a quadratic function. What told you that it was a quadratic function? Maybe you saw a squared as your highest power of x, right? Okay, so maybe you're helping a little cousin or a little brother and sister and you're telling them, this is an absolute value equation. What told you that it was an absolute value equation? You identified it because you saw those bars that we refer to as absolute value bars, right? We're going to talk about the same thing with exponential functions. What's going to allow you to identify a function as an exponential function? To do that, I want you to look at the word exponential. I want you to observe it. What do you notice about it? Did you notice the word exponent? Right? That's the root word of exponential, right? Pretty much. So exponent tells us a lot about the kind of functions when we can identify them, because our variable is going to be in the exponent. Now, if you're at home and you have the packet, you saw this form, the parent function, the standard form of the equation, y equals a times b to the x, okay? Where is our variable? In the exponent. In this case, it's x, but we also know that it can be any letter. You can see it frequently as t because it represents time in application problems. Also, on your packet, you saw that b was referred to as the growth factor. You will often hear me refer to it also as the base. It's both things. I may refer to the number in this spot as the base of the exponential function. So I wanted you to make sure that you knew what I was referring to. We have our a. You may or may not presently see an a in every problem, but that is going to be our initial value. And we know our initial value, especially when we looked at linear functions, that was our y-intercept. And then finally, we have y. Anytime we use a function, when we input an x value and we solve that problem, it generates an answer, right? And that is our y. So just a little touch of what was already in your packet. Now, we're really going to start diving into what is the parent function? What does the shape of this graph look like? You already know what a quadratic looks like. When you're practicing for the ACT and you saw that quadratic function and you were like, oh, that's a quadratic. What did you know about its graph already? Maybe you knew the shape was a parabola. You know it's like this, right? Maybe with the form it was in, you were able to identify the vertex. One thing I know that you would have known how to do is you would have known if the function opened up or if the function opened down, simply by just looking at the equation, because you've been taught to look for key characteristics like that. And we're going to develop that strong understanding into exponential functions as well. But before we can do that, we need to determine the shape, the parent function of an exponential function. So we're going to start by looking at f of x equals 2 to the x power. Remember, f of x is just function notation. We looked at it at the very beginning of the year. It's the same thing as y. Now, we need to develop this graph. Think about what are some different ways that we can graph. Our favorite way is probably a graphing calculator, right? But maybe you don't have a graphing calculator at home. Maybe your graphing calculator is at school. That's okay. Maybe we could use Desmos, right? Well, what if your device isn't working, or you live out in the country like me and your internet is just not cooperating with you? Maybe you only have a pencil, a piece of paper, and your brain. We can use a table of values, right? Okay, that's what we're going to do today to establish our parent function. We have a table of values, and we're going to go from -2 to 2. So to begin with this, we're going to evaluate all 5 of these into this function. And we know from previous math classes, even earlier this year we touched on it, that we're going to take -2 and we're going to replace it for x. So that means now that instead of it saying 2 to the x, our function is going to say 2 to the -2. But that exponent is negative and it's nasty. We don't like it. So we're going to go back to Algebra 1 to our exponent rules. I know they're a little rusty, so we're just going to pull them out and brush them off a little bit. What happens with a negative exponent? What do we do to make it positive, to make it beautiful? We're going to move it to the bottom. That's right. So now we have 1 over 2 squared. And tell me, what is 2 squared? It's 4. So our answer is 1/4, right? Okay, so -2 evaluated in the function 2 to the x is going to generate 1/4. We're going to do the same thing with -1. 2 to the -1. There's that nasty exponent again. We don't like that. So 2 to the -1, we need to move it to the bottom, right? And we're going to get a positive 2 to the 1, and anything raised to the first power is that number, right? So our answer is going to be 1/2. 2 to the 0. Here's another exponent rule that we may have forgotten about. Any number that we raise to the 0 power, no matter how big, no matter how small, whether we know the number or we don't know the number, any number raised to 0, what do you know about that? It produces 1 as the answer. Yes, you're exactly correct. So 0 is going to be 1. Now, 2 more. 2 to the first power. Oh, there. Well, it's not working. 2 to the first power is 2. There's the work right there. It was not cooperating, but we know that happens, right? Okay, and then finally 2 squared. You know that 2 squared is 4, right? Okay, so now we have completely filled in our table of values, but how does this table of values help us graph? You know it. You know that each of these levels translates into an ordered pair. So our first ordered pair is -2, 1/4. And you know how to graph that ordered pair. We're going to go out -2 on the x-axis and we're going to go up 1/4, right? And that's going to be our first point. And you're going to do the same thing for all 5 points. But I only have 30 minutes and I was feeling really nice, so I went ahead and did it all for you, right? And so we have all 5 points plotted right here on this screen. Now, one thing I want you to notice, I have 1 point and only 1 point labeled. Why would I have chosen that 1 point as the 1 point I would label? Why is that point important? It's the y-intercept, right? That's one thing that we discussed in our essential concept. That's one of the key characteristics that we want to be able to pull out about exponential functions. And in our parent function, our y-intercept is 1. Now, we know to finish out this graph, we need to connect it with a nice, smooth, beautiful curve. Okay? So now we know that our parent function is going to have a y-intercept at 1, and it's also going to have this nice, beautiful curve that kind of looks like a little bit of an elbow to me. I don't really know how exactly you describe it, but maybe it's a little bit of an elbow shape. But I have a question for you. Is there a number that you could pick for x that would make this function to the x 0 or make it 1? I want you to think about that. You're probably sitting there, maybe you're thinking, maybe you know the answer, but maybe you're sitting there thinking, you're like, I don't know, and that's okay. What we need to look at is we're going to start looking at this negative side of the graph because that's where it's getting closer to 0, right? This is where our answer to this question is going to be, maybe, because this side's going to positive infinity. It's not going to help us much. So we're going to go down the negative x-axis closer and closer to negative infinity and see if we can find a number. Now, when we look at our table of values, 1/4 was the closest thing to 0 that we could find. So I want you to think about what happened when we calculated 1/4. We said 2 to the negative 2, and what happened whenever we had that negative exponent? We had to move it to the bottom, right? So, and that made it positive. So no matter what number we choose on the negative side of the x-axis, what are we going to have to do every single time? We're going to have to move it to the bottom, right? Which is always going to make your exponent positive. When that exponent turns positive, what's going to happen to your denominator every single time? It's going to get larger and larger and larger, right? Overall, if we're talking about a fraction, how is that going to affect the fraction? It's going to make it smaller and smaller and smaller, right? But is there any way to choose a number on the axis, on the negative side of the x-axis, that would make this answer right here turn into 0? No, there's no way to raise 2 to a number and get 0. And even if we could, can we divide by 0? No, that makes it undefined, right? Okay, what else? So is there any way to make it negative? No, but what does this mean? What does this tell us? This tells us that there is an asymptote at y equals 0, a horizontal asymptote. If you look, I don't know if you can see it on your screen, but there's a green line drawn on this graph now, and that's where our horizontal asymptote is located. So now, our parent function, we know that the shape is an elbow-ish shape, but we know it looks like this, where it grows slowly and then it grows much more rapidly. We know that the y-intercept is 1, and we know that the horizontal asymptote is 0. So we just determined all of those key characteristics ourselves, right? But you may be sitting there and you're like, that's great, Ms. Jordan, that's really great. But how is this going to apply to me? Let's talk about it. How many of you plan to go to college one day? A lot of you? Okay, I know I always intended on going to college. So let's talk about what happens at colleges whenever they have to increase their tuition to compensate for the rise in cost that it takes to run their university. Now I want you to pretend you may be a sophomore in Algrbra II or you may be a junior, but no matter what classification you are right now for these next few minutes, you're a junior in high school. Okay, you've narrowed it down, you've done all your research, and you know which college you want to go to after you graduate high school. And you have found out, you know how much it costs to go to school there, and you have it all planned out. Well, you just found out that the university had to implement a 5% raise in tuition over the next 5 years to compensate for all the rise in costs that it takes them to run the university. So my question to you, now that you know that there's going to be a 5% increase, how much is it going to cost you to attend that school your senior year of college? Now, you know that the tuition is $4,000 this year. We know academic years begin in August. So fall of 2019, the beginning of your junior year, it was $4,000. How would you calculate how much it's going to be next year? Maybe you thought in your head, oh, I'll find 5%, which is $200. I'm going to add that to $4,000. It's going to be $4,200. Maybe you thought of it a different way. Maybe you said, okay, I know I have to pay the $4,000, which is 100%. I need to find 5% more, which is 105%. So I'm going to multiply by 1.05 and immediately get $4,200. Whichever way you choose is absolutely correct. If you came up with a third way, which I have no doubt that some of you may have because you are quite impressive, that is fine too, as long as you came up with $4,200. Now, the question is, how much will tuition be your senior year of college? This is your senior year of high school. So that doesn't answer our question, does it? Would you do the same process again, or would you change it? Maybe you did the first way. Maybe you did this two-step way and you decided to go into one step. But it's the same idea, right? For our freshman year, we need to figure out what is 105% of $4,200. That's $4,410. What about your sophomore year? The same thing, right? Which is now $4,630.50. What about your junior year? The same thing, $4,862.03. What about your senior year? $5,105.13. Can you answer the question now? How much will tuition be your senior year of college? Yes, you can. It's going to be $5,105.13. But I have another question for you. How much will it cost you to attend college for 4 years? I'm hoping you thought to yourself that you would just add these 4 numbers and that would become your answer. You wouldn't need to add all 6 because these first 2 years, you're still in high school, right? You're not paying to go to that university because luckily you get a free education. So we would add all 4 of these numbers and we would get the total of $19,007.66. I have another question for you. What would be the cost of tuition in fall of 2025? We had just calculated fall of 2024. I'm hoping that you thought, oh, well, it's the same as fall of 2024. Why would we not calculate what 105% of this amount is? Why would we not do the process one more time? Because the problem told us that it was just over the next 5 years. You had your 4 years of college, plus the first year, which was your senior year, which makes all 5 years, right? So the 5 years of increase have already happened. Now, maybe you're still thinking, well, Miss Jordan, that really doesn't apply to me because I don't plan on going to college, or I'm not worried about how much it costs. I'm going to get scholarships because I'm going to get an athletic scholarship. Good job. Or I'm going to blow my ACT out of the park and I'm going to get an academic scholarship. Great job. All of those are high goals and it's awesome. But I know something that all of us would love to have, whether we are planning on going to college or not. How many of us love to car shop after driving down the road? Oh yeah, even though I'm in a car shop every single day I'm driving, even though I love my vehicle. So let's talk about, you're in the market for a new car. So maybe you are coming pretty close to graduation. Maybe you're really hoping your parents are going to buy you a new vehicle as your senior graduation present. Maybe when you plan on graduating from college and landing that dream job, and with an excellent salary, and you're going to get an excellent sign-in bonus, and that's it. I'm going to get my car. But you want to make a wise investment. Or maybe you're just really trying to impress your parents with the amount of research that you've put into the car that you really want to get. Okay, now, we've narrowed it down to 3 cars. You've went car shopping. You've done the research, and you've narrowed it down to 3 cars. Ford Mustang, a Dodge Challenger, and a Lexus LS, maybe. Those are just 3 random cars. Okay, I really love a Ford Mustang, and my kids tend to like a Dodge Challenger. And why is it? Let's just dream shop. Let's look at a luxury vehicle, right? Okay, so we're going to do the research, and we found out that the brand new price of each of these vehicles, $21,000, almost $22,000, a little over $22,000, under $70,000. But we know we're not going to just keep this car for a year. We want to see how it maintains its value. So we want to research it, right? How well did a car that was 1 year old, okay, that is a 2019, has it retained its value? So we look at its 1 year old. But you're thinking, you have 3 ones right there. Well, sometimes things happen. Sometimes you're pulling in your driveway and a pecan limb falls and puts a dent right above your grill. Sometimes things happen. That happen to me. But we want to go ahead and plan wisely and know that things happen and our car's not always going to be in excellent condition. So we found the price for excellent condition, good condition, and fair condition for all 5 years, 2019, 2018, 17, 16, 15. But this really doesn't tell you much. So we're in math class. This is an Excel document. Guess what Excel does for you? It will create a scatter plot, right? How cool is this? Okay, we have a scatter plot for all 3 vehicles and the prices of their cars. But does that really tell you which car maintains its value the best? Because that's the question, right? So let's talk about something. What if there was a way that we could get Excel to generate a function or connect these with a nice smooth curve, that would give us a lot more information. Well, guess what? Those people at Microsoft are really smart, and we're a Microsoft school, and so you have access to Excel, and so you can do this project, and guess what? Excel has it written in there where they can create what's called an exponential function of best fit. Now you're probably thinking, that sounds a little familiar. In Algebra 1, you probably learned about a line of best fit, right? Okay, now this we're just applying to exponential functions. Now, what you're going to do is you have your table of values just like what we had here in Excel. And you need the age. If you notice I put age here, not year, and that was important. Okay? And it's going to create your scatter plot, right? You're going to have your scatter plot selected on your Excel document. Across the top, your ribbon selection is you want to make sure your scatter plot is selected and that you have the design tab selected. Now down here on the very far side, on the left side of your computer screen, you're going to see Add Chart Element. It's a drop-down box. You're going to drop down and you're going to go to Trend Line. And guess what's right there? Exponential. You're going to select that and Excel is magic. All of a sudden, you have an exponential function of best fit going through the data points that you provided, that you researched, that you discovered, right? And up here in the top of your scatter plot and your graph is going to be this function. Now it was really tiny, so I typed it over here for you on the side. $22,026 e to the negative 0.147. Now times x. Let's talk about this function a little bit. We know that this does indeed match our standard form that we saw on the very beginning. That's the first page of your packet, I believe. What is your base? It's e, right? E is what's being raised to power. What is your initial value? 22,026. Now you may be thinking that Mustang wasn't quite $22,000. Well, this is an exponential function of best fit. It's kind of estimating a little bit because it has these three values in here and it's trying to compensate for all of those values. So this number is going to be changed a little bit, but that's okay. Now here is our exponent and you're saying it's not supposed to have a number up there. It's okay. We're not going to worry about it. It's going to tell us something very, very important. This number is positive. E is an irrational number, just like pi, okay? It's on your calculator. It's positive. X is positive because your age is always positive. We can't have a car that's negative years old, can we? No. So what is really important is this negative number, negative 0.147. What is that number? It's your depreciation rate. So for a Mustang, the depreciation rate is negative 0.147, which can be rounded to that it's depreciating at almost 15%. Same thing with a Challenger. We have the same kind of equation generated here. We have an exponential function. It has a depreciation rate of negative 0.121, so roughly 12%. And then finally, our Lexus is depreciating at a negative 0.204. So we have all of our depreciation rates here. And my question to you still is, which car retains its value the best? Is it the Mustang is almost 15%. It's almost decreasing at 15%. The Challenger is 12%. And the Lexus is 20%. Which one of these is best? The Dodge Challenger, right? So we use these exponential functions to see which vehicle is the best investment for us, which of course we know that there are other things to consider. Insurance costs, maintenance, overall customer satisfaction. But that's how it applies to you. Now next week, you're thinking, that essential concept also talked about logarithmic functions. So that's what we're going to dive into next week. I hope you enjoyed this lesson. Stay safe and stay home.